It's actually that's not good. Yeah, I'm actually going to get some machine in a minute. The reason being is the chips actually get quite good. And you should see these go.
But yeah, because obviously you brought it up. So,
Yeah. So if you need any of this stuff, it's just.
oh, now yeah.
You go this stuff, other shoes.
Right now you
I use open scale as well. I use open scale. I do use open scale can be nice as well.
yeah. Well, I just use this.
Yeah. So that's it.
What's your
That's actually pretty hard. And I keep going on this, but I used to bring in the They are.
Next time on that. That's right.
Like I do.
Just thank you for the opportunity. Again, this has been really good. And you get, I've missed having people. It was great to do.
It's been an intention.
Yeah, that's right. Yeah, exactly.
Not what you see there, but that's starting.
What is the plan for tonight? So, finishes I was. You said about go downstairs, your name. Yeah.
Yeah, the main finish is 122.
Right. Okay. Yeah. Okay. Okay, so go downstairs, bike in there, come back up here. No, I'm going yeah, that's good. Definitely. Yeah, should be. This is close. A lot of people. No, I think what.
Yeah, so that's it's always kind of like, yes, I'm starting. Yeah. Yes, farming, like a fleet space. I'm so glad I'm here tomorrow. We've got a whole space exhibition, land in Newcastle, but also constructing up. I mean, it's good for testing. Yeah. Some of these history. And then going, aha, you need to talk to them, you need to put volume, you need to get yourself involved in right now. That's a problem. At a national level, presidents need to be talking to WIA saying, I need to know about this. You need to talk to that club over there. Right, and get the clubs to it. There's plenty of stuff out there, like these groups. I love the internet. I love the internet. It's full of cool stuff. There needs to be this. We are the unit some degree. Attitude that we engage with, I think. Go here, and there's every or searching. You can search for something and something. If you don't know those words, Then I started talking to other ARISS. I'll talk to you Friday night. Right? It's like this. I'm going to teach you to go to one. Friday night. Right? Then we have two. How about we look at stuff like that? Right? Free these comes out. And then I can see like 1 year, right? So I'm going to go to some of this long 23 seconds. And I think we spent the first hour talking to all the ARISS. We're going, hello! They were all known, you're on top of the hill. Oh, ready, mate, you're ready. Line up now Wellington, no matter what they line up, it's just everywhere, you know, they all talk about it. And you're like, is that right? So back when I was at university, it wasn't at the university. Yeah, so if you've got someone who works there, you know, getting those. All of these I work 2 days a week for Adelaide now. So I work with I'm trying to get facilities manager, roof plan, in the 90s, we started up there. I was just thinking, working on that. But that was funny. But what's funny is radio. Two boys sitting on learn something new. Yeah, it is. They've got a whole subject of research process. I mean, it's you demonstrate what happens to learn something. So all of our students class to talk all about their so they're all like, oh my god, you know, like, we're pretty lucky. I had one of those really nice chats. It's not there that some of the writing going to change. Oh, no,
Hello, online people.
Hello, Peter.
Oh, good. You're still there.
Yes.
Some of the calcium from the VK5, I've heard.
I'm asking questions a bit because there's 2 slides on the side. And then you have
When we said basically going from the architecture of
Well, thanks everybody. Since we've got everybody back in, we're actually making up a couple of minutes of time. Our next presentation tonight is from David, VK5KK, who we met in the forum earlier on today, so I won't go through his bio again. He's going to talk to us about the final frontier, 241 gigahertz, and his attempts to get us all operating up there. David.
Thank you. Good afternoon, all. Slides up. The laser pointers front.
You should have control that.
Okay, cool. Should. Oops, my surname's not spelled correctly.
That's my fault.
That's okay.
Is that quick wrong?
Easy on. Sorry, I put my glasses on. There we go. That would be on. That would be forward. No, that's the laser point. That's working.
Still no clicker, Pete.
So the blue light's coming on. Ah, there we go. Okay.
That was me, so.
Yeah, no worries. Okay, so I'm going to try and keep this so it appeals to the broader audience. So it's a lot of pictures, a bit of an explanation. It's really part two of what I presented in Tasmania. So this is we'll call this the complete rundown. The one in Tasmania, I think I'd got the chips about 6 days before the conference, so had basically just got it working, and it was only one working at that stage. So before I get going, yes, that's a spectrum analyzer plot actually at 241 gigs, and that's actually a signal on 241 gigs. As I go through this presentation, you'll see that minus 63 really doesn't mean anything, because what we're using to measure power there is not calibrated. 241 gigahertz, you can see further. So the something for nothing thing really resonates here, except it's reverse. It's a lot for not very much. So this is from Ian's website. Do yourself a favour, even if you're not into microwave, pop on to it's VK5 microwave.net. All the BOM data for every state's there, so you can see a live within 15 minutes picture of what your path loss is on 24 gigahertz and above. It is really good. So what I've done here is just plug some figures in with some guesstimates of what power is, minus 5 dBm power, 20 dB noise figure. And these are rough figures that come from the German data sheet. And for a 10 kilometre path, I think it's if we get anywhere near this is sort of meaning everything's working well. So we're yet to get to that. We've had signals over 8 kilometres, and that was well before we'd optimised things. So it's very much work in progress. 241, final frontier. It's our highest allocated band, above 300 gigahertz and up to the parts of the spectrum where Rex is working. It's free use, just don't cause any issues. Bit of history. May 2022, Indy offered me the 300 gigahertz module, which is a fairly old module. Turned it down, but they mentioned they were working on a more complex 240 gig radar front end. August 2023, they announced the first prototype, which was the 091, which is the, we'll call it the forerunner of the one I used. 2024, they did a second batch because there was a few things not working in the first batch. A number of the pins weren't working, but that's pretty normal when they do batches. There's a fab plant they use in Berlin. So, you make a small batch, find out what's wrong with it, fix it, and then do another batch. But then they also mentioned that was pre-production. I'd experience with the 31 chip for 134, which basically didn't work. So I thought I'd wait. And the 097 with more functions were released in 2024. And that was just before the last, the Tasmanian. So the chip, the first problem was no technical data sheet, and this is quite common. They basically showed me some of their spreadsheets and plans they had for the fab, so it could work out what the pins were doing and how to use it, but there's always a risk. So I went through a couple of different boards to the final board. The main changes were these pins over here, which didn't work on the early versions. They added a TX power control, They also added you can actually measure the RF. There's a detector diode in there. Goodness knows how they do this, but it's actually quite accurate. You get about 1.7 volts on that when you've got power. You can wind the power control up and down 20 dB. Don't ask me why you want to reduce your power on 241, but it's all there. So the chief chap design was really handy because they're sort of interested in what we do with stuff this was designed for measuring fluid levels over 3 meters, not trying to communicate over kilometers. This is the block diagram, and it is probably twice as complex, certainly far better technology than the 122 and 134 chips. The one improvement they've done is this VCO works on 13 gigahertz now. The other chips are at 60 gigahertz. So what I suspect, it's allowed them to use a better stamp, a better quality oscillator, and we'll talk about that a little bit later. They've also, it made it a really universal chip. You can get the LO out, which is great if you want a very expensive 13 gig oscillator, but you can also inject in an external oscillator here, or injection lock the oscillator. Now that I haven't tried. This I did try, but after measuring this VCO, it's pretty good. So it was no worse than a normal 13 gig VCO. And there's a switch in there, ×9, ×2. So it's ×18 to get there. The big improvement over the other chips is that they've got it's a coupler. It's not really a switch, but a single antenna. All the other chips have 2 antennas, which has always been a problem because the 2 antennas are 1.5 mil apart. 1.5 mil is half a wavelength on 122. So that introduces all sorts of problems. Here's the power detector. There's a temperature sensor, which is interesting. It for what I do, because it's narrowband, thermal drift's not an issue, but it's there if you want to do any thermal compensation on the VCO. Yeah. The receiver is much the same topology, so there is an LNA in there, so goodness knows where you get a 240 gigahertz stamp. The fab they use, I think, has access to some interesting things. So, and frequency doubler, IQ generator for the mixer, and IQ out. Interesting bit, this chip, the other chip is a 200 meg IF. This is tops out at 50. So we end up using, 100, I think. We ended up using 55 megahertz as the IF. Couple of reasons for that. We could use 50 megs, but one thing that Ian came up with, if you use a 705 and tune to 55, it won't transmit because it's in a general purpose thing. And the last thing I want to do is transmit up the backside of this chip. So that's it, all in one thing. So we're talking about a receive converter with effectively what is a modulated oscillator, whether you modulate that with A1CW or FSK, which is what we use, or digital. The data sheet turned up in February, March, and this time they did some pretty good plots. Once again, not sure how they measure this, on the power output and the actual noise figure. So they're roughly the figures I put in that spreadsheet to come up with a budget estimate of what it should do when it's working properly. And they're claiming anything up to 0 dBm. This is, and I think if you read the fine print, it says without antenna. Goodness knows what we're not expecting conversion gain with the antenna, although we have done polarization checks on it. It's basically a patch antenna, 2 triangles side by side, and it's at least 10 dB or more rejection when you turn it vertical. So it is horizontally polarized, which is better than what the other chips are. The other chips are sort of a bit, we'll call it ambi-polarization, not necessarily horizontal or vertical. So on paper, now it looks quite good. You know, we're yet to prove this, and certainly I don't have the equipment to measure either noise figure or power. But to be honest, it's been actually quite surprising to see, as we improve things and as we sort of learn about the chip, how far it's got using effectively a power head that's not even rated at half the frequency. This is the VCO, and this is probably one of the parts of the whole chip that impressed me, is it's a very linear tuning range compared to the 134 chip. Now the 134 chip has about 3 times the tuning rate at the top end as it does down the bottom, whereas conveniently the chip itself will operate between about 225 and 260, and they've settled the thing on 241. I just, from what I've seen on their other information they provided, they use 240 gigahertz optimized stamps. So for once we're using something right in the middle of where it's been designed to operate. And the 13 gig oscillator is nice flat thing. What that means is that they're calculating the filter. With the other ones, I had to basically change the charge pump to roughly shift the filter to be optimum. So in software, we use 2 different charge pumps for 2 different bands. It was just a very simple, probably the second filter I tried. The first one was just seeing where it sat in theory, and then just shifted some of the values so it sits mid-range for charge pump. And the setting of the charge pump in all this there's a fine balance between what is your residual phase noise and what your recovery signal is. So a little bit further, we'll look at that. But that's perfect for tuning. It's pretty typical of some of the Hittite or now analog devices, VCOs, that have a pretty flat tuning range in the middle. Very easy to work with. Oh, it's okay. So this is actually from last year. So this was the test setup. So there's a little power supply board there. There's the front end board. What I've done is on my system, the main board stays the same for all the bands. You just change the RF board. So that's it. And there's the W band sensor. So that's calibrated to 110 gigahertz. And just with the flange sitting right up against the chip. And that's basically what I used to do the plot you just saw with another off-screen supply. Click, click. Are good? Next one, yeah. There we go. So that was the filter calculations. In the end, the calculations are based on the frequency that's outputted by the chip. So there's a divide by 4 prescaler from 13 gigs. So you end up with 3.3 over there, 18 megahertz per volt, which is pretty normal stuff we're used to doing for like 13 gig, 10 gig, 13 gig PLLs. And there's the filter. Fairly simple filter with an OP184 op amp that's pretty typically used for all these PLL designs. So in the end, that was the second and final filter. I think for the other ones, I tried about 5 or 6 different filters to get a balance that I could steer with charge pump. Charge pump, I'm not sure what it shows up there, but it ended up being about 3 milliamps in that sort of, I think I had 2.4 there, so it ended up being 3.
Next one.
Next one, yep. Now the other bit is the reference. So in the previous designs, very early we used a 10 meg reference, but the whole point of using a high frequency reference is to reduce your phase noise. On the 134, we use an 80 meg one. So if you just click, you probably click, there's a few drop downs, just click 4 or 5 times, bring the text down. There it is. It's the same size as an Arduino Nano, and those that have seen the board, it sits underneath the board, the Nano's on the top, and it just sits on the same pins as the Nano because the Nano actually programs it. Next one, there we go. That's fine, just at that. This board I already had in place for the 134 one with an 80 meg oscillator. It's a third overtone oscillator, so quite a clean. They're typically used for microwave phase lock loops. ADI software calculated that 125 was the upper limit for a phase detector without having to divide. So, and I found 120 megahertz was common. So that's what we ended up with. And that's the plot. Offset at 1 kilohertz, about minus 107, which is a little bit more than what the data says, but that's still pretty clean. Effectively, that pegs one of the 3 factors in the phase noise. It's interesting. Once you start testing a few of these things, you find there's other limiting factors. That's running it without a micro running, without a battery running. So the whole aim is to get that the same as when it's sitting on the board, that's actually measured on the board. One more click, and that's the plot. So near in is about minus 80. The limit of the analyzer is what's here, but this, in theory, would keep going down. Next slide. That's the finished unit. Just a few things to point out there. There's the nano sitting on the top. That's a 90-degree hybrid, which does the IQ separation. That's the chip. So it's a 5mm by 5mm chip. The actual antenna is offset, it's under the plastic, but it's offset 0.5 mm below the center, which is, there's never anything simple with these things. It's great for what they're doing, but in the end, I made another board with pushing the chip up by 0.5 mm, but never used it. You can do these things in antennas, especially when you 3D print them. That up here, not populated on this one, but that's where you injected external local oscillator. In the end, decided that the oscillator on there is good enough. And this is just simply the pi matching. Single-ended IQ out. What we found in tests, that's more than good enough to get 13, 15 dB rejection at the lower sideband. That's all you need to gain 3 dB. That's the test setup. So sitting there with the horn, one of these horns, butted right up against the flange of a 110 gigahertz W-band sensor. A lot of the work from this point on was actually getting a clean 10 meg reference. That once you get everything sorted out in the gigahertz end, it's the other bit. And jitter is the thing that you really, it's your real enemy at this frequency. And those that want to know about these PCB devices, that's where you get them from. Handy if you've got scrap plastic around, you can use lots of colours. See how we go for time. Oh, yeah. So I think the next slide is going to show us some plots. Okay, there's the signal and no cal. In fact, I could have dialed in a cal. That's default 30 dB. This head at 122 is about 55, 56 dB, and probably at 241, who knows. The bit that is impressive here is that we actually can see the noise floor. That when we first started, we couldn't see the noise floor, so you got no idea what you're doing as far as working on the main signal. And yes, that's been averaged, but it's around about minus 41, minus 42 dB at 2-3 kilohertz either side. So that's to put that in perspective. The best we've got on 122, 134 is about minus 48. And given that every time you double something, it's 6 dB more, it's the same result. So that's I think we've got as best we can get there. The importance of this is that you want as much power as possible in that central carrier. When that line's at 30 dB, a good percentage of your power is going into noise. And that has two effects. Obviously, your main carrier isn't actually as strong, and you can adjust the charge pump. You know when you're getting to the right spot. When adjusting the charge pump is only making a fraction of a dB change in that. When it's noisier, the charge pump, you'll see 2-3 dB. So you know your noise is effectively your power is. So if you're only 30 dB out the noise, most of your power's in the noise. Reciprocal on receive with the IQ mixers, the less injection you have, the IQ mixers at some point stop working. The receivers become very deaf. So we've achieved that in the last 2 weeks, 3 weeks, I think. It wasn't like that when we were doing our first test. So I don't know what that level is, because what we're doing there is a horn. up against the flange. So the capture area of the waveguide is 3%, 5%. So you could probably do the numbers, but to me, the fact that we can see it on like that, it's working somewhere near where it's expected to be. Next one. Here's an actual noise plot. So reference level at the top. So you can see it sits 3 kilohertz, 30, 300. It's effectively, there's a bit of a bump out there, and that's about where the filter peaks. So it's a pretty flat sort of noise, and then it tapers off out the side here. That's not fantastic, but if you look at the actual fundamental 13 gigahertz oscillator, once again, the increase in phase noise is 20 times the log of the multiplier, or roughly, for every time you double, it's 6 dB more phase noise. That almost exactly lines up to what the 13 gig oscillator looks like, except it's about 90 dB down there in phase noise, which is about what you get from a Coon or whatever that thing. So it's where it's going to be, and it's not going to get any better. Now, this is, we use, Ian's software runs it all. So my bit's just the hardware. So this is the serial output, and you can use, there's a number of different serial programs you can use with Arduinos. So we just use the Arduino. So we'll call it the tuning tool. And what's on the left here is the menu, and it gives you a bit of an idea of what functions can be remotely controlled. There is auto detection of the 10 meg oscillator, because once 10 megs drops out, the PLL goes into tri-state, so it just runs with the free running oscillator, which is great for doing measurements, but not for accurate readout. You can calibrate. There's a little diode on the 10 meg input, so you can calibrate the input. Reason for that is that 10 meg references people use can be anything from 1 volt to 4 volts, 0 dBm, whatever. So there's a calibration level. We might be able to get away with not using that anymore, but it means there's a switch. So if it gets below a certain point, which is like down below where there's random noise, it'll take the PLL out at 120 megahertz. Call signs go in here, messages go in here. This is where you enable the digital modes. So we can now do JT4, JT9, or my favorite, Q65. And yes, you can use FT8. I can tell you now that FT8 doesn't work on 241 and probably not going to bother with it. Q65, especially 60E, works really well because there is a bit of warble there, and there is a bit of lock time with the PLL, about 20 milliseconds, but it's long enough, slow enough to work. And we've not tried in the field yet, but on the bench with signals you can't hear, it works quite well. The other parts of it, this is the normal menu you see up here, so you can have 1 of 4 frequencies. And we just 241.1 call channel. You can QSY to 150 if you want to, just in case someone else is on 241. 242, I did a sweep, and the power output there is about 3 dBm higher. And that's probably a combination of different things or whatever. Maybe the power isn't higher, but it's, that's sort of perhaps the frequency we'll use if things really get a bit rough. But I don't think there's any problems with Grant Spectrum playing up there. We FSK, so that's the key up frequency. And that's the local oscillator. So 55 meg IF, 120 meg. These you can change in the program here. If you can do the divide by 2, but there's no need to do that because the phase detector, it all works out for 120 megs. Call signs in here, grid. So it has the same setup, memory 1 through to memory 6 to do a QSO, exactly the same as WSJTX. So first one's CQ, second one's calling, third one's report. That's confirmation, that's 73, and that's CQ. So very simple. These are the bits that I've used a lot of. There's actually a sweep function in there now, so you can sweep across and check the range of the VCOs. And the two, and these are the only two, the two have slightly different locking voltages. There's other test modes. You can look at the various parameters. You can toggle high to low LO. So we use that to check the image rejection. It just flips and you can add a number in to actually, because when you flip, it's going to go to not quite the same frequency. You can dial in same frequency. There's a test mode, which is like a dee 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 dee. So if you know.
The test mode just shows more information while you're operating.
Oh, okay, yep. Ian, this is all Ian's work, this bit. It's very, you know, if it wasn't for this, it'd still be me with a Clipsal key. And you can actually, because there's various things can be turned on and off. You can turn the pin to the front on and off. You can turn the IF amp off if you want to. I've never tried that, but I think on strong signals that probably actually would act like a. It's probably it could be handy as a 40 dB attenuator. Not that you need an attenuator in 241. So this is extensive. Full stop. Arduino Nano Every is such a. We started with the original Nano, and we've ended up with the Every. Okay, so I better move along. So everything, yeah, JT4, FT8, Q65, and right, and that's what the normal screen looks like with frequency readout, and that's when you hit 24, gives you all the parameters, and there's the charge pump current at 3 milliamps, negative bleed turned off. That's what Q65 looks like. And this is on just, I said before that I don't use KK for digital, so you'll see ZMKZ, it's my dad's old call sign. But that's Q65, 60E decoding on 241. "3D printed horn." I'll leave these up afterwards so you can have a bit of a look at this, but most of the challenges have been actually finding, getting an antenna that was going to work, especially with an offset antenna and with this little patch thing, which is about 0.8 mil across. It sits in the same holder as the lower frequency one, so you can just line up on 122 and it's usually about 5 and 9 plus 20 dB or something, and then go to 241 and it's 5 and nothing. So there's Edmund reflector, Cassegrain 3D printed. That one there's probably, you can either use, we use foil to start with, but that's with silver coated copper, but you'd use the nickel. You know, it's beauty of the nickel stuff, the spray and stuff. Okay, it's expensive, $80 a can, but it's so thick, it fills the gap. So you do one spray, give it a wet and dry 1200 rub, and then do another one, you get a perfectly smooth surface. Very reflective Edmund dish, bit of a problem. I've got a slide at the end to show what can happen. This is like another subject on its own. So this is some of that's the final one there. That's a rectangular one, and that little pick, you may ask, what's that for? To put the copper, so this is adhesive back copper. You just wind the copper around with a sticky on the outside and push that in, and that perfectly sits the copper in. A conical one for that bit. There's a bigger one there, which I tried, and it was just too sharp for the Cassegrain. That's actually on 134, and that's a little tube adapter we did to use with those lens antennas that were on 60 gigahertz. And they work, but the gain's far less than what a dipole is. Questions? Now, before we do that, I've got enough time, haven't I? Do a practical demo. Just one more slide. That's what happens when you leave the dish sitting on your back seat and it gets a bit of sun on it. Probably a bit hard to see because it's black. All melted here and bent. Now the sun would have hit it at an angle like that, but there was enough heat reflecting off the surface to start melting the plastic. So in one of our QSOs, which wasn't going very well, it was the Cassegrain was bent. So what I'm going to do now is do a quick demo, plug all this in. There we go, Tom.
Is that everything?
Yep. Okay, you can hear me? there. Got there. Put that one there. Just any message.
Right, okay, wait a minute.
Oh, you're calling me? So they're designed to be radar chips. So that's. It's a bit more Doppler on 241 than what you get elsewhere. Yeah, it's quite interesting. I won't point them at each other, but they're quite. And that's just the auto key. The tone is not T9, but that's where the original tone was about 500 hertz wide, and there's still a bit of warble on there. It's about 18 hertz, but that's. You know, we're not going to try and get anything better. It's certainly good enough for working with Q65. So that's my presentation. Any questions? I'll just turn that down.
It's not running. Justin, you're banned. He's gone. Any questions from the room?
Okay. Last year I put a cost up, and that's why I'm not expecting, and this very educated question from Tim over here was probably how many hundreds of 122 one should help?
Over the two runners of the 100.
Over the running of the 122 gigahertz project, we built and delivered 600 modules worldwide to 30 countries.
Yeah. So the chips were €22 or thereabouts, weren't they?
Yeah, they were.
Yeah. These are 700.
Oh, okay.
Okay, that's the end of the session. They did not cost me that much, and you know how they work. But they're very keen for an article to be published. But the reality is, they're a venture-funded company. Their 134 gig chip failed. They've taken it off the website. They've got 800, so plenty for amateurs around the world to do work. These they made about 100, yielded 87, of which 2 are sitting here, and they've still got plenty. But you know, in the end, they've got to make money, and I think every time you do a fab like that, it's probably best part of €100,000. So that's how they worked it out. Cool. Any other questions? Not after that. Thank you, guys.
Thank you, David. So, our next presentation is on deep space reception, and I'm going to invite Trevor, VK4AFL, up to to speak. Trevor's been licensed for 65 years. In 1960 as ZL2APH while still at high school in New Zealand, and he then became ZL1AL, a call sign that he still holds. And he's been VK4AFL since moving to Queensland in 1989. Trevor's primary interest now is in weak signal line of sight microwave, DX and EME work. Trevor. So there's a laser pointer here.
Just have my timer.
And that's back and forwards. Okay, we'll get your slide presentation.
And to advance it is...
There's 1 and 2, forwards and back.
Okay, thank you, Kevin. I started out as a shortwave listener in the mid-50s, and it looks like I'm going to end up as one 70 years later. So amateur deep space network is concerned with the detection of extremely weak signals from distant spacecraft, which can, for a lot of people, be a bit intimidating. but as I'll explain later, it's not as difficult as it sounds. S-band and X-band systems are the most common. S-band is in the 2 gig range, and X-band is 8.4 gigs. There's a 50 megahertz segment. Also, Ka band is used up to 32 gigs. The first 32 gig experiments, which were experiments at the time, was in 2012. Initially, NASA thought that signals coming back through the atmosphere might not work, but it works very well. And the big advantage, of course, is the higher frequency you go, the bigger, wider bandwidth you can use. Demodulation of science data is generally not performed because it's pretty difficult, but it can be out to perhaps about 100 million K. There is software for it, but it's certainly not easy. Yahoo Amateur DSN is used as the focal point. There's a deep space network as a forum, is used as the focal point for activity. There's also another organisation, DSES, Deep Space Exploration Society. And they were formed after someone found in Haswell, Colorado, a 60-foot dish, commercial dish, of course, that hadn't been used for, I think it was about 20 years. So they ended up inheriting this, and over a period of years rebuilt the motors and position indicators, and they've now got it working very well. Right, why would you want to do it? Self-improvement from a technical perspective. Spacecraft orbital mechanics is a very interesting topic in itself. Learn how to build and optimize receive systems, and I'll come back to that, optimizing receive a little later. Precision frequency and time standards, and to experiment with software-defined radio for weak signal detection, and which is mandatory. Before I got into this, which was about 18 months ago, 2 years ago, I had no experience with software-defined radio at all. I hardly knew what SDR stood for, but it's mandatory. And of course, to detect spacecraft millions of kilometres from Earth is another reason for doing it. After the first presentation this morning from Otto and Finn, I thought that this would be a very good something that you could promote to get young people interested in amateur radio, or in this case, shortwave listening. There's no exams to sit, there's no regulations, and it occurred to me this morning that this would be something very good for someone, people in that category to get into, and I'm referring to young people. Right, there are 4 DSN ground stations, 3 in Madrid, Goldstone, California, and of course Canberra here in Australia. They've each got at least 4 antennas ranging from 26 metres to 70 metres, and they've got these antennas working, or they operate in the S, X and Ka bands. And I've already mentioned that NASA are moving towards 32 gigs for greater transfer rates. We better not let Donald Trump know about this. Funding for Canberra is paid for by NASA with an annual budget of $20 million. NASA, in fact, funded the original installation at Canberra. in time for the 1969 moon landings. If there had not been a space program, then NASA wouldn't have existed, at least not at that point. And in fact, Canberra was the first ground station in the world to recover signals from the moon. For the California base, based in Pasadena, California, on the outskirts of Los Angeles, and the annual budget is $26 billion, or $500 million a week. There has been naturally talk with the new the administration, and again, our friend Donald Trump is trying to knock some of that on the head, and maybe he'll succeed. All right, two types of space vehicles: those orbiting a planet, and those vehicles on the way to a planet, asteroid, or a planet's moon, which is known as cruise mode. Distances involved: Mars currently around 300 million K. It varies between 300 million and about 100 million and about 400 million kilometers. Jupiter ranges between 600 million and 900 million kilometers. So we're talking pretty serious DX. Right, the equipment required at amateur level. Dishes as small as 1 meter are used. 2.3 meter or bigger is the norm. I have the picture here. This was a dish removed from a household TV reception, satellite reception dish. That's 2.3 meters. That would be ideal, but you can go smaller. And accurate as L drive with position reporting, accurate to within about 0.5 degree. And a feed to suit right-hand circular polarization. All of the spacecraft available are right-hand circular, transmit in right-hand circular. There is only one, I don't know the reason why, but there is one that transmits in left-hand circular. So I have received that one by changing I don't have any instantaneous method of changing polarization, but I was able to alter the feed to suit left-hand, and I was able to detect the signal. Low noise preamp, e.g. 0.8 dB or better, with about 28 dB or more gain. I'll elaborate on this. A down converter from 8.4 gig, we're talking X-band here, of course, to an IF frequency, and an SDR displaying waterfall results on a PC. What we're doing as amateurs, of course, is competing with these ground stations. The Canberra antenna weighs 3,500 tons, and their LNA, cryogenic cooled LNA, costs $30,000. So that is what amateurs are competing with. I use a Kuhn 8.4 gig down converter, which I've mounted at the actual feed. It has a claimed noise figure of 0.8 dB. When I bought it, I initially ordered also a preamp, which also had 0.8 dB noise figure. So the Kuhn down converter has optional 35 dB gain to 50 dB gain. So what I ended up doing, I thought, well, if the preamp and the down converter are the same noise figure, you don't need the preamp, especially with 50 dB gain. So I just mounted the down converter at the actual feed point. When I looked at what when I initially got interested in this and looked at what the big guns are using, which is always a good start, I noted that there was a lot of emphasis on bandpass filtering. And I thought, why actually do you need that unless it's used for image noise? But with a 1200 meg IF, image noise is so far attenuated that you don't have to worry about it. So it's a pretty, just use a pretty simple setup. This dish had a C-band feed, so just the down converter mounted on that. Right, pointing information. Sorry, I'll get back to that. We'll go to the next one. Right, Tianwen 1 is a Chinese spacecraft orbiting Mars. When this screenshot was taken at 336 million K, and as you can see, it's not a weak signal by any means. I actually checked this spacecraft about a week ago, and I was receiving it at 34 dB above the noise. So we're not in a weak signal, not really in a weak signal environment. Now this is a bit more serious DX. Juno spacecraft, NASA spacecraft, which is orbiting it's in a polar orbit of Jupiter. Most orbits are equatorial orbits. The reason it's a polar orbit is because the radiation from Jupiter is extremely intense and it would damage anything that's currently available. So they lessen that by utilising a polar orbit. This is about 5 dB above the noise and 933 million K, and the light time was 51 minutes. So it is pretty good DX when you consider that a signal from the moon one way is a bit over a second. So this is 60 times that times 51. The dish I use is a 3.7 metre meshed dish. Right, the ability to resolve a signal can be defined by 4 words: signal to noise ratio, irrespective of whether it's audible or you're detecting it. So the idea is to build, and I have an EME, a reasonably extensive EME background. So the trick is to build a low temperature noise system. Now, when comparing results of a dish performance or any antenna's performance, that we're talking here with a dish at this frequency, there's 2 things. There's one is sun noise, the other sun noise Y factor, which is the sun noise compared to the ground, or a 50 ohm, better still a 50 ohm load, or cold sky versus a 50 ohm load or the ground. Now, the most common comparison that operators make is that they, amongst each other and comparing performances, is that they compare sun noise. And really, it's the cold sky to ground that you are looking for. A benchmark is somewhere in the 5 dB to 6 dB range. 6 dB is very good difference between cold sky and ground. My system, I've measured it at 5.3 dB, which is not bad. And you can probably work down to about 5 dB Y factor, cold sky ground. If you're able to improve your system by, say, 0.1 of a dB, that doesn't improve the signal to noise ratio by 0.1, it's about 3 to 1. So if you could improve your coal sky Y factor, say by 0.3 of a dB, you would end up with about 1 dB better performance. 1 dB doesn't sound like much, but in this environment, it's quite a bit. Now, the noise that you're competing against, when I say coal sky, the sky is pretty cold at this frequency, but there's also a fair bit of noise from various cosmic noise from various sources, pulsars, etc. But the most interesting noise and the most distance is remnants of the Big Bang, which is easily seen. Some of this is remnants of the Big Bang. I don't know, is that 4 billion years ago or something like that? Anyway, it's very good DX, well, whatever it is. So, critical aspects, building a system to overcome path loss. We've already talked about that. DSN ground stations receive in the 110 dBm to minus 110 to minus 150. You obviously want accurate tracking and position reporting. Sun can be used in a bigger system, or thermal moon noise. On my 3.7 metre dish, I'm at 8.4, I'm getting about a dB of moon noise, just as the moon is a radiator. It's actually not, for the size dish I've got, that apparently is not all that hot, but because I've seen greater claims. But anyway, I get a dB, so that's it means that something is working. Now, a problem with spacecraft reception, some spacecraft operate all the time with a carrier. Others only operate in response to an uplink. Now, it's very difficult. In fact, it's almost impossible to find out the program for that. So now, carrier suppression. The reason why you can't hear some spacecraft, even though the distance might suggest that you should, is because there's too much carrier suppression. And it's carrier detection is what we're after. If there's no carrier, you won't receive anything. Just getting back to this screenshot, this was received at a 1.5 hertz bandwidth. I use an S by R2 SDR with, and I've never used anything else. I don't really know much about it, but it works fairly well. Anyway, that's a 1.5 hertz bandwidth. All right, how to locate a spacecraft. We know they're up there. How do you find it? Well, sites such as DSN now, these sites show current status of spacecraft being communicated with. And the important one, the number 3, is JPL Horizons, which is a NASA-funded, free, available to anyone, gives pointing information, visibility, range, and Doppler calculations. Now, there's a fair bit of Doppler associated, or can be a fair bit of Doppler associated with this. In the case of Juno, the one with 933 million K, midpoint, which is its greatest relative velocity, you're looking at about 750 kilohertz of Doppler, which is a lot. The first spacecraft that the first spacecraft that I detected, which was a fairly simple one, I didn't know anything about this. I just tuned around and happened to stumble upon it because it was a very strong signal. And information regarding spacecraft and their frequencies is available online. Okay, how are we going? All right, we're 22 minutes in. Just get this back right. If you're looking for a new project, I can absolutely recommend this. It's easier than EME. I've had about 27 years experience with EME. Not an expert, but experience is something. And this is actually easier. If you're deciding whether to go EME or DSN, this is definitely simpler. No transmitting, of course, obviously required. Basically, you're a sophisticated shortwave listener, is the bottom line. And as I mentioned earlier, I think it would be this would be a good incentive for younger generation, and that's, well, sort of the theme of this conference to some extent. Excuse me. The 3.7 metre mesh dish I use was simply a TV reception dish. I bought it from company in Acacia Ridge in 2005, cost $360 then. The exact same dish now, wait for this, from the same company is $2,600. And unfortunately, my income hasn't gone up in that same proportion. And I know, of course, we could talk about this all day for power bills and everything. Well, that's probably about 23 minutes. I'll just run through the list here. I think I've got everything. Oh yeah, pointing. Now, for the Juno spacecraft, hey, who's that? It took me quite some time to find that signal. Can I just have this again? Took me quite a long time to find this, and initially I thought, well, simply my system was not up to it, but it was because I was not pointing accurately enough. Now, with this particular signal, 0.4 degrees off either way, which is not much, that totally lost. And to put 4 degrees in perspective, if you drew a circle and had 900 increments, 900 lines on the circle, okay, 0.4 is one, moving one of those lines. The Canberra 37 metre dish, they have their half power bandwidth is 0.04 of a degree. I don't know how they maintain that. Mind you, at 3,500 tonnes, it's not going to blow around in the wind or anything, but they must have some pretty sophisticated system and software to get that lined up. And the best DX that amateurs have ever achieved is with deep space, in fact, is the best DX of all, and that's reception of Voyager 1 spacecraft. It's been done about 4 times by amateurs. The first time was in 2008, I think. Louis Capito, CT1 GMK, I think. He received it when it was at 14 billion K range with a 5 metre dish in his backyard. He said it was actually amongst fruit trees and things like that. Not only that, he only had linear polarization, so he was a 3 dB hit there right away. And a lot of integration time is something that I'm trying to learn. I know what integration does and I know why it's used, but I don't know how it's achieved. Perhaps someone might be able to tell me a bit more about that. More recently, hams have detected Voyager 1 now at 25 billion K. I think we're looking at 18 hours of light time. Something astronomical figure, pardon the pun, associated with that. And reception from Voyager 1 is the absolute amateur milestone. You cannot do anything better than that, simply because there's nothing further out. Okay, all right. Well, I think that concludes. Okay, 27 minutes. I think that is really all I've got to offer on it. But I'll just reiterate: if you're looking for something to do, this is something that you can do with spectacular results with relatively minimum effort and cost. Gary, 4GU, developed a system. Basically, he homebrewed everything. He's got a 3-meter dish, did it with very minimal expense, and he received a spacecraft about 5 years ago orbiting Mars. The range was 256 million K, and I saw it. I couldn't believe it. I thought, how's this possible? Okay, well, I've nearly had my 30 minutes. Thanks for listening. Thanks for being here. And I hope someone can maybe get interested in this.
Thank you, Trevor. Fantastic. Isn't it amazing what can be done? Have we got any questions in the room? Quite a lot. Good. We'll get Scott.
You might have to relay.
We'll get Scott running.
I've got a bad case of tinnitus at the moment.
You're right. What we're going to ask is if you can stand up and name and call sign as well, just for the viewers online.
You might have to relay.
ENVK5ZD, do you know what modulation scheme the spacecraft use and what the bandwidth of the signal is?
No, sorry, I don't know. No. Oh, that was an easy one to answer.
Okay, next, Rex. Again, stand up and name and call sign.
I've got that.
Rex, VK7MO. I presume you have to GPS lock the whole system.
Just relay that.
GPS locking? Do you have GPS
locking? Sorry, I forgot to mention that. Yeah, no. To further add simplicity to my system, no GPS locking at all. The frequency is varying so much with Doppler shift. I sometimes wonder about but I have not. The Kuhn down converter that I have does not have provision for GPS locking. The later version does. The AirSpy R2 has provision for GPS locking, which I tried, 10 meg reference, and it didn't improve anything.
Okay.
Oh. Sorry.
All right. Was there anyone else?
Yeah.
Andre.
Thank you. Andre, VK4ANL. You showed some waterfalls. It looked like the frequency was increasing.
You can really.
I'm assuming that was Doppler.
The slope that you had on your waterfalls, is that
Right.
just Doppler?
Yes.
Is it just Doppler?
Yes.
And how do you know it's just Doppler and not your own system that's moving?
Okay, well, you know it's, you can know it's Doppler. Well, it's supposed to have Doppler because the relative radial velocity is changing. And in the case of that Juno one, I think I saw there was an decreasing frequency. Doppler is determined by, of course, the relative velocity between the observer. But to add something else to it, of course, it's also influenced by the Earth's rotation. So it's not just something going from A to B. the B part, the A is you're turning with the Earth as well. So there's an interaction between the two. And JPL Horizons, the website that I mentioned, will give you the Doppler information required. Be pretty difficult to calculate without that.
Thanks. Any other questions? Right at the back.
I just wanted to add to the question before about decoding and the modulation schemes here used. There's a really good piece of software called SatDump. I'm not sure if I don't think it provides anything for Juno and stuff, as I don't think anyone's gotten signal strong enough to actually work with it. But it provides a really good set of decoders for pretty much everything amateurs have been able to get strong enough to decode. I'm not sure about a lot of other deep space stuff, but pretty much anything that you could try and get a strong enough signal to decode is offered by SatDump. It also includes some stuff, I've forgotten the satellite, but I think it's got some lunar reconnaissance orbiter stuff in there as well.
I got some of that. I'll get Kevin to relay.
Otto's saying that there's software program called SatDump. Have you come across that?
No, I haven't.
Okay, yeah. That's all I just wanted to say. It's very useful software for anyone interested in sat stuff.
Okay, well, thank you very much, Trevor. Very illuminating experience and well done on a fantastic achievement. It's amazing what can be done.
It is amazing what can be done with, with relatively simple equipment. And thanks for your 32 minutes of your time.
Okay, thank you. I was just going to phone my mother. So for our final session this afternoon, we're going to move offshore. We're going to listen now to. So I'll just get everything in place here. We're going to move across to Denmark, and we're going to hear about the future of VHF and microwave beacons. And I'd like to welcome Bo Hansen, OZ2M, who's going to talk to us this afternoon. Bo, can you hear us? We can see you. We can see you on the screen, and we can hear your voice. So it's over to you, and we'll take questions at the end if that's okay.
Yeah, that's fine with me. Especially for a hybrid presentation, it's usually necessary to have the questions at the end. Normally, I would actually appreciate it during the presentation. It becomes much more live and interactive, but that's fine enough. Welcome to the real OZ. Let me just bring up my presentation. I wonder if, hang on a second, just take time here, share. I think I'll do my presentation this way. It's a bit easier for me instead of having the presentation. I hope it's okay with you guys.
Yes, it's arriving perfectly, Bo, here in Brisbane. So please carry on.
Good. Because it's not full screen, especially for these online presentations, it's a bit more difficult. Anyway, thanks a lot for having the opportunity to talk about the future of VHF and microwave beacons. The presentation I'm going to show you, I'll take about, say, a holistic approach, very much related to the experience that we have with those at 7IGY, sort of taking the whole idea of should we do something and so forth. Then I'll talk about beacon technology, digital roads. That's also one of the things that I understand was that you'd like to hear about. And then also the synchronized beacon project, which is a 6-meter beacon project, but it could in reality be used for other bands as well. There's nothing as such related to the specifics of being on 6 meters. Anyway, the whole idea about beacons, at least seen from my point of view, and perhaps also from the users at least, is who do we build the beacons for? Who used the beacons? Is it for the builder's own ego? That could be one approach. Should it be for, say, extremely high, technically competent engineers, or is it just for, say, the listeners? The reason for doing so is that we had a history in the OZ7RGY working group that we wanted back in 2009, say 16 years ago. We did discuss if it was time to add some new functionality to the beacons, not just say remote monitoring and so forth, but also was it time now to include some kind of new digital modulation. So we did discuss in the working group whether it's the ideology of technology or the uses. Is it just for, say, the sake of digital? Should we go full digital or whatever? And the approach that we did was actually to ask all the users, what do you want? What do you use the beacons for? And so forth. So we did kind of a, say, normal market research to understand what was going on. And we concluded that there's 3 or 4 different types of uses. At least in a, say, Danish or North European context. It may be different in Queensland or in Australia, but at least in those days, and it pretty much stays the same way, even though the digital users have increased in numbers. But we have these 4 or 3 different groups. FM users, they really don't care about beacons. They may have heard of it, but usually they are just, say, on say, two-way communication types of operation, or they may use repeaters. They may become a digital user, and that's probably more likely nowadays than it was, say, 15, 16, 17 years ago. Then there's the analog DXer. They are very well knowledgeable in propagations and beacons and so forth, and they may not have a single point of interest into digital communications. Okay, this may also be changed, but there is still a large group, and some do regret the digital aspects of it. Now, then there's the mixed mode. I mean, they probably just use whatever it takes to make a QSO. They understand beacons, propagations, and so forth quite well. And then there's the digital user, say the new species. They are there for digital communication. They may not really understand propagation, but over time they will learn more about it, and they could move into these kind of mixed mode operations group. And by doing so, they also become much more aware of the propagations and beacons. However, my experience is that there is a tendency among, say, if you have the transition from 3 to 2B, that's a really large portion don't really understand propagations as such. They say, okay, I have a signal, that's fine, that's all that matters, but there's a lot more to it. So how did we do it with us at 7RGY? Well, we did a research among users, and I went to several VHF and micro meetings in Northern Europe to collect responses, not just from local users, but also in a more international context. And the response was that it should stay the way it is, just CW and carrier. And some said, no, it should only be digital. Some said, more carrier, less carrier, no carrier at all. And there was even a request for it being just an EME training beacon. In those days, it was JT65B. And there was also somebody who said that, or it's not just individuals, there are more responses to each bullet here, though. It's very important that it's the same sequence all the time. The reason for this is that there were some beacons I think there's still maybe some in the UK that has a asymmetric sequence in even odd minutes. Frequent identification signal, and the only thing that you're looking for is some kind of identification. And one of the reasons for this is also I've made a CW beacon keyer many years ago, and I've had really weird requests that it should set the website URL, QSL manager information, and so forth in CW. And from a DH's point of view, it's really nonsense, and it takes a lot of time, and the frequent identification really drops to the floor. Then it should also be decodable via Aurora or ray scatter. OZ7 IGY comes back from or originates from 1957, the International Year of Geophysics, and we still wanted it to be able to decode it via Aurora with the digital modulation. Then it should also fit into the existing beacon spacing. That's, at least in the European context, it's 1 kilohertz slots. We cannot have a wider frequency use, even on right-wave bands. And then, also very importantly, that if you listen to the CW part or the digital part or the carrier, you should not have to retune every time. And then some people say, yeah, we want to have a 1 kilowatt beacon, and some say, no, it should only be milliwatt level. That's an ongoing discussion, whether it's a digital or just say classic beacons and so on. Should beacons be something that you could hear prior to normal stations being able to communicate, or is it just for the local ones? Then say a watt might be fine, at least in a VHF. But the conclusion, that was very clear. Same sequence all the time, 1 minute sequence, and it's not either or. It's not just digital or CW. It's digital and CW and the carrier. So, what's the beacon technology? Well, in the old days, it was land mobile or PMR equipment. That's also something that applied to OZ7 IGY. They came in abundance, but one of the drawbacks of doing so is it becomes typically very much, say, a one-man kind of modification. It's only the guy who did the modifications who can actually troubleshoot. So yes, it's cheap. You have everything in one box, and it's fairly easy to modify most of them for CW and carrier. Another way could be actually to have, say, a baseband transceiver. In these days, you'd probably use a Raspberry Pi or similar, and then mix that so forth. Can it be locked? It might be a little bit more difficult, at least in a digital context. Nowadays, we do tend to have a preference to beacons that are, say, locked one way or the other, whether it's a video standard or GPS or satellite, whatever. Then it's possible, and that's what we did for us at 7 IGY. We decided to embark on a design path to have our own hardware platform. It's a lot of work. I think we spent around 8,000 hours designing it in the beacon group, but we had it the way we wanted it. And that's one of the clear benefits. Another benefit is that by having, say, dedicated hardware and software for that matter, we could use the same platform across all bands. So it's a lot easier to maintain, and that's quite crucial in a beacon cluster where we have 12 beacons from 10 meters to 24 gigahertz. Now, speaking of dedicated hardware, we designed the next generation beacons platform, actually the one down here first. There is no doubt, and this is what it looks like, that's the exciter alone. Then the GPS geo comes to it, and a 1 gigahertz clock, and all the rest of it. But it's kind of a Lego brick system. It's by far the best beacon system that is available. Some says it's the Rolls Royce of beacons, yes. And if we compare it to the RF0 that I think most of you, or some of you at least, are familiar with, It's, as I say, it's 10 dB more expensive, but it's 20 dB better in every way. Then some of the things that that we also heard, especially when you look into, say, the cheaper platforms or the cheaper technology, mentioning the SI5351A, a lot of people, they focus on the harmonics. Well, harmonics, as a regular amateur, we know how to deal with harmonics. It's not difficult. It's just a low pass filter or a band pass filter. And that's illustrated down here in the arrows. This is the typical approach. That we can just focus harmonics. They're down here. That's not a problem. The low pass filter, they're gone. It's much more difficult to get rid of the in-band spurious. And that's illustrated here. Yes, we do have high harmonics, but in this case, the in-band spurious are much lower, and that's what matters, and phase noise and so yes, it's possible to do with cheaper electronics, but in the end, you get what you pay for, especially in, say, high integrated circuit kind of design. You do get the functionality of the integrated circuit. And there's not a lot you can do around it. Of course, you can cater for it, having good supplies, good supply isolation, good PCB layout. So, but the internals of the chips, you cannot do a lot about. Then, if you do decide to build a new beacon, whether it's classic or say a new dedicated platform, there seems to be a lot of focus on the hardware cost of the beacon, the electronic hardware cost. But our experience is not just with the IGY beacons, but also all the users of the next generation beacons platform, and I think there are around 25 of them, and the others are such where there are hundreds. There tend to be an underestimate of the effort that goes into building the beacon. Our own experience is, yes, if you get the hardware for the beacon itself, the electronics hardware that we supply, for instance, then you can still see into, say, 25 hours of work per beacon. Then there's a site preparation, and so there's a lot of work going into it. The hardware, electronic hardware itself, is nothing in comparison to the total bill of both work and money. So yes, the electronic is the least effort. On the picture, you can see Henning as a 9GE and Michael as a 2ELA working on the next generation beacons. Signed this back in 2010, I think, the pictures. So, what's the learning points from OZ7 IGY? Share the effort. It is extremely important. Ivan OZ7 IS, who's very, very committed to OZ7 IGY, and has been that for decades, was a one-man band for about a decade or so. But he has managed to continue his commitment to it. But still, we learned that nobody can be committed forever. It has to be a shared effort. And in that context, it's extremely important that the beacon platform across all bands is as identical as possible. It makes it a lot easier to maintain. And financing. How do you finance it? It's one thing to put the beacon up and running. Many beacon groups or individuals are very committed to this in the beginning. But after a few years, then that may not be the case. Then it perhaps becomes a one-man band. If it's a one-man band, he may even have to commute several hundred kilometers. There are even some beacons in Greenland where you have to fly in with a helicopter. That becomes very, very difficult to maintain, and it becomes very people or individually focused. So how do you finance it? For us at 7RGY, we have events like we have today, the VHF meeting. We have T-shirts. We go to flea markets and sell stuff that we get donated and so on. And we get some entrance fees and so on. So we managed to keep the OZ7 IGY operations afloat by, say, sponsorships one way or the other. Now, if we talk about the digital modulation, then unfortunately, I experienced that comes from different user groups, as mentioned before. There are some who think that any modulation or the one that they prefer, a lot of times it originates back to Whisper. Whisper will decode on 10 gigahertz. Yes, it will, no doubt. But how often will it do it? Can you have a higher link probability by using a more robust mode? And this is what this slide shows you. If you go to an ice rink, it may not be that relevant in an Australian context, but still, then wear a pair of skates. If you're going to play football, wear a pair of football boots. If you go hiking, then wear a pair of hiking boots. There is no single modulation that's good for any kind of modes. However, the conclusion from our experience is that if you want to have something which can deal with unforeseen or unknown conditions, then you should wear a pair of hiking boots. Because there are no free lunches when it comes to sensitivity, flexibility, robustness, speed. It all goes hand in hand. You cannot have one single mode that fits, or say one size fits all. And at least in a commercial context, the only thing that matters, that's the link probability. Yes, you can have a lucky punch strategy that you could decode, say for instance, Whisper on 10 gigahertz or 47 gigahertz in a 1% incident. Then you may conclude Whisper works on 10 or 47 gigahertz. Yes, it does, but not as frequent as a more robust modulation. And in that context, it also becomes relevant how fast do you communicate and how robust is the modulation. And in this slide, I have two comparisons, and the graphs are made by K1JT, and it shows FT8 and FT4. And a lot of people say FT8 is a lot more sensitive than FT4, and indeed it is, under the right circumstances. The graphs here show or the comparison here is that under heavy distortions or path irregularities, FT4 becomes a much better modulation. That has to do with it's only 4 tones and it's a shorter duration primarily. So if the path is heavily distorted, then you have a fraction of the signal and the total signal takes a less time, then FT4 becomes a better modulation. So it's not just the, say, raw sensitivity numbers, given that it's average white Gaussian noise AWGN, it's all the path irregularities that also comes to play. So my point is that looking into these sensitivity numbers alone is really, really nonsense. FT8, yes, it's good, and you can have a lot of communication going on. It's very, very good on 6 meters and below. On 2 meters, yes, it may be good enough, but then you may have to change mode. And for say stations, regular stations, that's fine. But for a beacon, maybe not. Then back to those at 7 IGY, we decided PI4 modulation, and I'll come back to that in a minute. But the whole point is we wanted a general purpose, same 1 minute sequence, and we also had this Aurora range scale requirement. So we decided to go for our own modulation, and it has been very, very successful. Nowadays, Q65 has similar characteristics. It has a lot of sensitivity, again, under white noise conditions. It can also withstand some distortion, but it has a higher requirements due to the number of tones on the equipment. And is that a good idea? It may be, it may not be the case. Then Whisper, quite popular, but it requires smooth conditions. And yes, you can have smooth conditions even on 10 gigahertz for a very short period of time. So please take this into account that the raw sensitivity numbers may not be relevant if you're not familiar with the conditions. Do you want your beacon just to be successful 1% of the time, or should it be an overall, say, good pair of hiking boots that can take you anywhere? I think that should be part of the discussion of a new beacon design. Now, speaking of PI4, one of the things that was a requirement was that would fit into this 1 kilohertz slot. And you can see here in the green box, that's the space that we could operate or place the tones in. And since we wanted to have good robustness, a white tone spacing that you can see on the lower side is important. We can compare it to the right side, where there's just say 1 pin or 1 channel, if you would like to call it that, FFT channel. Then if there's a distortion between the transmitter and the receiver, then you will see that there is some frequency shifting. It may be instantly or typically a bit more sort of slow moving. But if you have a white tone spacing, then it may be less critical if you were, say, on the next or the adjacent channel. Whereas if you only have, say, 1 channel separation, then it becomes a lot more difficult. So that's part of say, the robustness. Then again, it's also a kind of speed thing. When can this happen? Well, in a kind of multi-path propagation. And a range scatter, if we talk microwave or aurora, if we talk, say, UHF range, then there are a lot of different paths. And what's illustrated here is that there's a direct path, yes, but there may also be a second or, say, heavy multipath cases going on. And in the heavy multipath, then the signal may be all over the place in all the different channels or FFT bands. And having, say, a wide tone separation may help in this. When it comes to decoding, then one of the, let's just go back one slide, one of the ways that can actually decode things is that you look in this particular pin or the channel to see if there is a signal. And during, say, distortion, then you may also have to look in the adjacent channels, plural, to see if there's a signal. And based on this, you can actually wiggle out. So you don't have to have a wider channel to keep everything in, say, in the sensitivity area, or the area to search for, sorry, because that will reduce the sensitivity. If you increase the bandwidth, you'll have less sensitivity. So you should still, in the decoder, look for the adjacent channels or FFT bins. And that can help in this respect. So even during heavy distortion, there can be a lot of, say, decoding things involved, which is not inherited in the mode itself as such. It just provides the possibility that you can look in the neighboring channels. Still, the decoder has a lot to play in this. Now, we decided to have this mixed mode sequence. And also the tuning should be identical for all parts of the sequence. I tried to illustrate in the lower right image the different modulations and how they are centered around, say, a typical CW carrier. And we decided to design the PI4 modulation so that it would fit into the normal tuning of a CW beacon. And one of the reasons why is that, as you can see from the picture at the top right, is that our ear versus age drops in sensitivity. When you're 60, and if we look, say, around 800 hertz, which is around here, you have about 10 dB worse sensitivity in your ear compared to when you were 50 years old. That's quite important because we very much did not want it to be just a digital beacon only. So we should still be able to hear it, and that's the reason why that we don't want it a high pitch. 1270 hertz centered in those days, it may be down to 1 kilohertz now, but still there's a lot of sensitivity loss, and you can benefit from having, say, a low kind of tone zero among all the different tones that is in the digital ultraviolet. So the PI4, there's a lot of numbers in here, but it's derived from JT4, so it should be really easy to implement. It has a wide tone spacing, sensitivity around 22, 23 dB, but again, it also comes to the decoder. 60 seconds sequence, and it repeats identically between the different minutes. Having the exact number of symbols that we have, it makes averaging really, really easy. We can discuss this afterwards if there's more interest in this, but basically this is the metrics, or these are the metrics for the PI4 design. Now, how successful is PI4 in a European context? Well, back in 2018, I did a presentation for the RSGB convention, and back then, half of all digital beacons in Europe were using PI4, and the numbers at the bottom of the page shows the same numbers, but also across different frequencies and most from July 2023. And as you can see, it's 48% that uses PI4. So finally, the synchronized beacon project. As I mentioned in the beginning, it's a concept devised for 6 meters. Even though it's, say, a region 1 idea, the idea is to have it in a global context. It's 10 time slots or 10 channels per continent or per region. 5 beacons in a 1 kilohertz register. And 150 beacons will then do for a full minimum rollout. But again, just like in cellular systems, you can actually have a frequency reuse, so you can have many more beacons. And the idea is that 1 beacon transmits in a 1-minute cycle and then waits for 4 minutes. If you're familiar with the International Beacon Project on HF, it's the same concept. And Finland, they are planning to use it on 2 meters with 10 beacons, and that's possible. And the RF0 that I mentioned in the beginning, this one here, was actually, or the reason for designing it was that we wanted a cheaper platform for 6 meters, say in a mass rollout, and that's the reason why it's designed. So that's the presentation. If you have something more or for some further readings, please follow some of the links here. There's actually a video of my presentation, which is a lot more focused on PI4, the digital modulation from the RSGB convention, and there's also got to the VHF Managed Handbook and the bigger project and so forth. That's the presentation.
Well, thank you, Bo. Just to let you know, it was received perfectly here, absolutely crystal clear in 5 and 9. I'm going to just see if we've got any questions here in the room that we'd like to put towards you, and I will do that now. Have we got any questions in the room? Just to say while we're sorting that out, we have a little experience of PI4 in our own beacon chain here in Brisbane, and our new 2-meter, 6-meter beacon, or the latest iteration of it, is running 2 RF0s, and we're trying PI4 mode as part of that 60-second sequence. The idea of having a fully coordinated system across the whole country is quite intriguing. Well, let's see if we've got any questions for you here in the room. Actually, you've got everybody spellbound, and we don't have any questions. So I'd like to thank you very much for taking the time. It must be very early in the morning for you to come on the air and talk to us in Brisbane. Good night from us, and thank you again for participating in the Q65 conference. 73. Yes, goodbye from us all. Well, ladies and gentlemen, that brings us to the end of the first day of the conference. As you know, there's a table booked downstairs for 5:30. It's a completely ad hoc arrangement, so do the best you can, but it should be good. For those who are wanting to come and participate in the ISS link up this evening, we've got the students and their parents coming here to the venue from around 6 o'clock. We're expecting the ISS path to be around about 7 or just after 7, because it is absolutely essential for that very short 10-minute link up, that when the process is going on, that whoever is here keeps the lowest possible sound levels that we can in the room. So I'll be stressing that with the visitors in particular, but what we can't afford, as Pete said earlier, is for a question to be lost because of some extraneous noise getting to the audio system and having to repeat questions, meaning that somebody may lose out on the experience of talking to the astronaut. So everybody is welcome, of course. I would just ask you if you are coming, just to be here well before 7 o'clock. Sorry, well before, yes, before 7 o'clock, maybe 15 minutes to. And we look forward to seeing anybody who comes. Let's hope that we get as much success with that link up as we've done with everything else today. So thank you all for coming on the first day. Starting tomorrow is at 9 o'clock, this first session tomorrow, and we so hope we see you all here then. Have a nice evening. I think last time I saw you was up at Tommy Ember's house.
It's not actually, it's not unusual. I just, the first one lasted for a couple of years. Just sit there, back to
It's been brilliant. Oh, thank you. So these need to go back on charge overnight.
That's the same with the rest of
The other thing I'm sure too is
to disease and the growth of plants. Over.
Well done, Max.
This is Kasha. What are the emergency procedures if something were to happen on board the ISS? Over.
Yep, very good, Kasha.
This is Jade. What kind of research is being conducted on the space station and why is it important? Over.
Yep, well done, Jade.
This is Ruby. If you could design anything to add to the ISS, what would it be? Over.
Yep, that's very good, Ruby.
This is Zara. How does the human body respond to the various changes in space? And when astronauts return, what symptoms do they experience as their body acclimates to the back of gravity on Earth? Over.
Well done, Zara.
This is Max. What studies are being conducted on the ISS to measure radiation levels, and how does that impact human space exploration? Over.
Yep, very good, Max.
Max again. Are any of the crew members twins, and are you part of any research regarding this? If so, what are some of the observable changes occurring? Over.
Excellent, well done, team. Yeah, I think if you can maintain those audio levels when it comes to our live contact, there won't be any issues at all. They'll be very good, very easy for the astronaut to understand.
Thanks, Shane. Appreciate the encouragement. I think the second run through was even better than the first, so well done, guys.
Yeah, no, that's really good. Well done, Michael. Done well. Okay. Stephen, any comments from your side?
Yep, all clear from me as well. Only observation is just a minor thing, is it might have been easier if everyone was standing up rather than having to jostle in the chair, but that's personal preference. Everyone did a great job, so it probably doesn't matter.
Okay.
I guess I just have to make sure that they move, like Shane mentioned earlier. Once they ask their question, if the next person can get in the seat ready to go to ask their question, while the astronaut's answering.
Yeah, every second does count.
Yeah.
And then, of course, right at the end, basically what I'll do is I'll say something along the lines to the astronaut. This concludes our list of prepared questions. I'll now pass the microphone over to Kevin Johnson, VK4UH, who will say a few words on behalf of the group. And then, Kevin, if you can do your bit.
Yes, I'm there ready to do that, Shane, so we're all standing by.
Okay, no worries. I would suggest, I'm not sure what you've got planned, but you're probably going to have about 10 seconds before we lose signal.
Yep, we're prepared for that, so let's just hope that the link comes up. Thanks, everybody, on the link up tonight to make this possible for us. It's going to be a good evening. Huge storm going on here in Brisbane at the moment, and I'm hoping it's not going to interfere with anything. Thank you, Shane, and thank you, Simon.
No problem. No problem at all. Well, we've got 38 minutes and 57 seconds to go until we have a direct contact with the space station. So we've got a little bit of time to kill, and hopefully the storm will hold out until after that period.
Just remember.
This is always the hardest part, the wait, to sit and wait.
Yeah. So yeah, obviously, unlike the run through we just did, there's going to be a Johnny answering the question, and so you'll have a bit more time to sit down and get a position, and obviously wait for you to finish and say over before you start answering. Ask you. Make sense? We can't do that good at all. I don't know the answers to all of you. No, we'll be fine. So, if you need to go to the toilet or anything, you want to drink or chat to your folks, now's the time. But I would be saying, when do you start? It's T minus. When do they need to be back in? Yes.
It's very daunting.
Yeah.
It's like very used to it.
Yeah.
More especially and talk to national. It's just a big
All right, so guys, sound hit. So if you're back, you need to go get a drink, use the toilet, back in your chairs. In 15 minutes at 10 to 7. Okay? Thanks so much for all this. Sorry. That's all right. It's Wavell Stadium. Yeah. They're our opposition. Yeah, so this is the schedule of Wavell services. So Wavell Stadium. I might just rise because I think once, yeah, I think some of them do you think we'll get through all the questions? So they know the process and they've got prepared. Oh, right. Okay. Well, we haven't. We're a bit more prepared. Some of them. Yes. But they're conscious. They're very conscious.
The duration of the pass is incredibly predictable, and they know exactly when
So do we, it's being filmed, do we get it?
massive also
now I've got the response. So I did ask a couple of weeks ago if you wanted to scan it. I had a pretty good day yesterday. Check my emails, so I have hard copies here. I'll give them to you. I can take them back to work, but I'll give them to you. So yeah, just yeah, that's what you've just been through. Oh, T minus 7.5 minutes. So here I give a bit of a spiel about who we've got. Yeah.
So they'll count down to all of these stages because they're seeing the space station come up across, they know exactly where it is. Then they'll make the signal what it
So I'm just gonna that's where I chime in. May as an ex-student, well, she's representing Chermside Guy.
Ah, yes.
Do we have any other questions? Yeah, Miss Cell's on the camera. Oh, okay. So I think we've got, you can ask a comment from the students except for a couple. Oh, okay. Right, okay. Did she? So she's just using my comment.
Yeah. I read it. It's like mine.
What is it? But she could. I thought you were going to ask. Because we got the right clearance and everything. Just have to check. I think they all have photo permission. They all have photo permission, but some don't have comment, so they can't make a comment. Yeah. Hi Jane, nice to meet you. Oh, did you have Mr. Brewer? No. He only went last year, and he was a student there.
Graduated in '67.
Yeah, no, he would have been there when you were there, unless he was training or something.
Maths. Oh no,
Okay. Mr. Bright, we've got a Mr. Bright there now, but he's different. Oh, Price.
Just noting we have about 30 minutes and 45 seconds until acquisition of signal. Okay, that's 23 minutes.
Thank you, Shane. Got that.
And about 23 minutes until we start official proceedings.
Yeah, so.
Julie, copy that. Thank you.
And whereabouts in the USA are you, Julie?
I'm in North Carolina.
Oh, North Carolina, okay.
The others are trying to make comments.
No, let's go. Wait. Wait, so you're going to go to the table? Yes. Wait, Grace. Get in the room. I don't need to be in it. Yeah, you do. Come on. I just want. I just like we knew. This is we're gonna make our YouTube really. Yeah. Oh wait, sorry, stay back. Oh yeah, I think we probably want the microphone.
Do we look at you or do we pretend like we're?
Do I need to like look at the camera? I should look at the camera.
Oh, okay. I thought it was like a generic.
I just realised we're not wearing our UQ Science Ambassador badges. So
I don't know where mine is.
I lost mine too. Can I? Ruby, look back. Hang on. Sorry, I'm circling my over so I remember it. Yeah. Just like hold it. No, just like.
What do we want in our report?
I think this is not wrong. I think we can have a whole photo.
We have rain here now, Stephen.
Do you guys want pictures too? Because we need to let them like.
Did you say you had rain?
Yep.
Okay. One for me at the moment.
Only white.
I don't know why. I feel like that's enough.
We look at the genies, you know how they're really
That's really good. Oh yeah, that's so nice. Oh, that is so nice. That could be on the Do you want me to take any photos of you, Jane?
Yeah.
Yeah, I like that. And tell me.
Incidentally, everybody, the display that's up on the projector at the moment shows the current position of the space station. The yellow orbit is the last one, the one that's complete, and the white orbit. The white orbit that you can see with the space station currently over Africa, that's where the space station is now, and you can see the path that it's going to take and come across us here over Australia in due course. So we'll be counting down from that, so you'll be able to see exactly where the station is as it comes over the horizon here. You can see the line between the black and the blue there, that's the terminator, that's the difference between, or the boundary between daylight and daytime. Daytime and nighttime, I mean, so you can see that we're already in the dark, but Western Australia is not yet. And when the ISS follows the white line and comes across the top of us, that's when we'll be in sight of and we'll be in contact with the space station.
I love congratulations. Wait, what's wrong? There was someone in there and she was like, I was so yeah, I loved it. Like, the meetings, I thought they were actually really good. Yeah, yeah, you know, it's not too bad. Like, not every year, most of the time, well, basically, yes, like this last week. I feel like it's kind of fun planning it actually. Yeah. There's definitely like a lot of things to do, like, sorry. I'm sorry, he has one, It's true. I know. Yeah,
Okay, just noting we're about 18 minutes until acquisition signal and around 10 minutes and 30 seconds until we start official proceedings.
Copy that. Thank you.
Noted, thank you.
Yeah, I do work. And you,
Kevin, is it all right if I just say something? Hi everyone. I just wanted to take the opportunity before the link up to thank Kevin and his colleagues at the local chapter of the Ham Radio. I'm sorry, I don't know the full proper name.
School name wrong, so that's fair enough. VHF group.
From the Brisbane VHF group, the Chermside group here, for giving our students this opportunity. I think it's a true once in a lifetime thing to be able to talk to someone live. Even if it doesn't go well, I think what we've already experienced tonight is something that you don't just get to experience very often, if at all. So I'm really proud of these students for having taken the opportunity in front of them. And yeah, I hope you remember it long into the future. It's really great to be given the opportunity, and I think I'm going to blow our own trumpet here. The profile that the science faculty has at Wavell is a good one, because we try and do engaging things and promote that within the community. I get to talk a little bit about the students a bit more later on, but I want to thank people braving the weather tonight for getting them here, and for family and friends, siblings, aunties, uncles, but also teachers from Wavell who've come along to support these students. So really, thank you everyone for coming. Thanks Kevin and everyone at ARISS and the Ham Radio people for providing the opportunity. And I'll just remind you that once the hookups ready to go or happening, please make sure your phones are silent, and we've been really, really quiet as much as possible. I will be talking later on, but I just wanted to take that opportunity before we get properly started. Thanks again. You can talk again now.
So you can see on the screen that the space station is winding its way across us. So the white line is the track that it's going to follow. The yellow line is the previous orbit. The green circle, incidentally, is what's called the footprint. That's the ground that can be seen from the space station at this instant in time. So when that footprint comes over the top of us, that's when we'll be in contact.
So This one. This one. I feel it pushing through. It's pretty bad anyway. So we'll just leave it as
We have about 10 minutes until acquisition of signal, and in about 2.5 minutes we'll start the official proceedings. Everyone can stand by.
Copy that.
Thanks, Stephen.
it'll be fine. You can get that occurrence in it. These aren't naughty kids. Why is that? Yeah. So you said 10 minutes, so it must be about a minute. It's getting close. It's very exciting. Have you done it before? Do you get to speak to the space station? Right. Okay. So the quicker we get through it, the better. That's going to be good. So the conference centre is here, but Stephen's in front. So where's Stephen? Right. He's just in there.
Okay, Julie, if you can please start the recording.
Thank you. This is the operator. I would like to inform conference is being recorded. If you have any objections, you may disconnect at this time. Thank you. You may begin.
Thank you. Hello everyone, this is Stephen Vassallo, VK4 SJV, your ARISS moderator for today. Through the help of amateur radio volunteers and the crew on the ISS, we soon hope to establish radio contact with the International Space Station as it orbits more than 400 kilometres above the Earth over Australia. This is all accomplished through ARISS, amateur radio on the International Space Station. The ISS is currently approaching the Australian southern coastline, travelling along at around 27,000 kilometres per hour. The contact for today will be performed using the ARISS Telebridge network, a worldwide network of amateur radio ground stations that enables students to contact the ISS. ARISS is an international consortium of volunteers from several nations that assist to develop and operate the amateur radio equipment on board the International Space Station. Some of those that support ARISS are the American Radio Relay League, the Worldwide ANSAT Amateur Radio Satellite Corporations, the Canadian Space Agency, the European Space Agency, the Japanese Space Agency, Roscosmos, the Russian Space Agency, and NASA. The amateur radio ground station that will establish radio contact with the ISS today is VK4 ISS, located in Mackay, Queensland, Australia, and operated by Shane Lind. Thanks for helping us out today, Shane.
It's a real pleasure from this side. Thanks, Stephen. Good to be a part of it.
Okay, we have about 5 minutes and 40 seconds until contact time. Our ARISS link up today will be with students from Wavell State High School in Queensland, Australia, attending the annual QTech Amateur Radio Technical Conference. Now let's check in with the group. We've asked HOD Science teacher Michael Drago to please tell us about the students participating this evening.
Hi everyone. We have students from across grades 7 to 11 participating tonight. We have boys and girls who've taken the opportunity to take part in this once-in-a-lifetime event. We'd like to thank everyone involved for the opportunity. We also have students who are our UQ Science Ambassadors taking part, and I'd like to thank all the students and all their families for getting them here tonight, especially with the inclement weather that we're having in Brisbane. We're very proud of our science program at Wavell, and just thanks for affording this opportunity to our students. We really appreciate it. Over.
Thank you. So how many people do we have in attendance this evening, approximately?
We have 2 teachers asking questions, and we have 11 students, 2 of which, 2 students couldn't make it, but their questions will still be asked.
Okay. And so what other preparations have you made for the contact?
We've had a couple of run-throughs this evening. Students submitted questions a few weeks ago so that NASA could approve them, and the questions are quite varied and reflect, the interest that the students have in this part of science. Over.
Okay, great. Thank you. And how did you become involved in the QTech Amateur Radio Conference?
We were approached by ARISS to be part of the opportunity tonight. There was an email that I received in January, I think it was. I went and sought permission from our principal, Mr. Luke Ferdinands, to see if we could take part, and of course, we took the opportunity with both hands. Yep.
Great, thank you. Okay, we're about 2 minutes and 40 seconds until acquisition of signal. Shane, the VK4 ISS, before the contact begins, can you please tell us about your station, where you are, and how you'll handle the conversation?
Okay, fine. Thank you, Stephen. And welcome everyone to this evening's event. Okay, so a little bit about my station. It's an amateur radio station, ARISS ground station, located in the suburb of Andergrove in Mackay in Queensland. The station is equipped with satellite tracking antennas that will automatically lock on to the International Space Station as it comes up over the horizon, and will continue to track right through until loss of signal. Now, we're quite hopeful that with this particular pass tonight, we'll get close to 11 minutes of coverage. The ISS, at its highest point when it passes over me, will be at around 86 degrees, so it's almost directly above me. The expectation tonight is that we'll have a good, strong, clear signal. It may take a little while to establish that signal initially. Often after the first 10 or 20 seconds, the signal might sound a little scratchy, but once we've established that contact, the signal will eventually get better, and we're anticipating a nice, good, clear contact today. Okay, back over to you, Stephen.
Okay, thanks, Shane. So we're about 1 minute, 10 seconds until acquisition of signal. So before the space station comes over the horizon, just remember what we're doing on the ISS is an experiment, so we can never tell the results, positive or negative, until the experiment is over. And students, again, don't forget to say over at the end of your question. So in a short time, the station will be coming over VK4 ISS ground station. So it's over to you, Shane, and good luck.
Great, thank you, Stephen. Okay, so we've got about 40 odd seconds before I get acquisition of signal. So if everyone can be in their positions, what I'm going to do, I'm going to start calling a little bit early. Don't be too concerned if I don't get an immediate response. I'll just continue to call until such time as I've got a response from the astronaut. Okay, so if everyone can be in their positions and standing by, and I will start calling. Calling NA1SS, NA1SS, NA1SS. This is Victor Kilo for India Sierra Sierra, VK4 ISS, calling for scheduled ARISS contact. Can you receive, over? Calling NA1SS, NA1SS, NA1SS. This is Victor Kilo for India Sierra Sierra, VK4 ISS, calling for scheduled ARISS contact. Can you receive, over? Calling NA1SS, NA1SS, NA1SS. This is Victor Kilo for India Sierra Sierra, VK4 ISS, calling for scheduled ARISS contact. Can you receive, over? Calling NA1SS, NA1SS. This is Victor Kilo for India Sierra Sierra, VK4 ISS, calling for scheduled ARISS contact. Can you receive, over? Calling NA1SS, NA1SS.
Victor Kilo 4 ISS, anyone looking forward to our conversation. Over.
Okay, NA1SS, this is Victor Kilo 4, India Sierra Sierra. Can you receive, over?
Victor Kilo 4 ISS, this is NA1 ISS. I have you 2 by 5. Over.
Okay, NA1SS, this is Victor Kilo 4, India Sierra Sierra. Okay, can you receive me okay now, Johnny? Over.
Victor Kilo 4 ISS, I have you much better now, 5 by 5. Over.
Okay, thank you, Johnny. Are you ready for the first questions, I'm assuming? Okay, students, please go ahead with the first question.
Hi, this is Michael asking a question on behalf of Louis. What types of experiments do you do up there, and how do they affect things on Earth? Over.
Hey, Michael, great question. We do a lot of different kinds of experiments, anything from studying biology, physics, medicine, and even material science. All of these studies help us better understand not only just science for ourselves and our bodies, and how we respond to microgravity, which in time is going to help us get out further to the Moon and Mars. Over.
Hi, this is Sam speaking. I'm very fascinated by the prospect of humans traveling to different planets.
How is the research that is currently going on in the space station contributing to the advancement of technology that would allow interplanetary travel? And how could a high school student in Australia be involved in this currently or in the future? Over.
So think of the ISS as camping out in your backyard and going to the moon or Mars as this crazy expedition to the Alps. You need to learn how to prepare yourself for austere environments, and that's what the space station does for us. It's a test bed for living in space, how our bodies react, and how we're going to conduct operations when we're really, really far away in Mars. As a high school student, my best advice is just pursue what you're curious about. Like, always stay passionate about learning, and it's going to take you places you never thought you'd imagine. Over.
Next question.
Hi, this is Isabella. What was the most unexpected thing that you experienced when going to space? Over.
The most unexpected thing was how much I would love just floating and flying in space. Never, ever gets old. Over.
Next question.
This is Sia. What is the biggest scientific question you are trying to answer with ISS research, and how does it help people on Earth? Over.
The biggest and most important question we're trying to answer is what we can do to optimize humans living, but not just living, but also thriving in space for long periods of time. And so this includes not just physical, but mental. And understanding this is going to help us conduct further missions out to Mars. Over.
Hi, this is Nima. What recent technological advancements have made space travel safer or easier? Over.
So we've had recent companies like SpaceX that have developed technological advancements such as automated docking, which decreases human resources and increases safety. We also have had improvements in life support systems, so we're able to reclaim most of the water, and even pretty recently have had technological advancements, the brine processor assembly, which can even further help reclaim water from urine. Over.
Drew here. What was one of the most coolest or interesting things that made space so much special and important? Over.
We're traveling 17,500 miles an hour, so we do an orbit around the Earth every 90 minutes. And when I look out my window, I get to see the Earth in the very, very thin atmosphere. And it's a different view every single time. It doesn't get old. Over.
Kisa here. Why does your hair behave the way it does in space? Over.
So in Kisa here, living up in space, we are subjected to microgravity. And so without gravity, our hair kind of does whatever it does. My hair is pretty short, so I don't need to worry about it too much, but I do have a crew member who has longer hair. And it's very fun. Over.
This is Sophie. Can you describe the moment or feelings you felt when you first saw space? Over.
Oh, it was just speechless. It was very emotional, very, very beautiful. And, not only is this the blackness of space so profound, but also just how bright blue our planet is. It's one of the most beautiful things I've ever seen. Over.
What kind of physical training and conditioning is required for you to become an astronaut and be selected for a mission like this? How long did you train for, and are there certain tests you must complete? Over.
So the life of an astronaut is always either supporting or training for a mission or actually being on a mission. Now, specifically for this mission, Expedition 73, I started training about a year and a half. And so that, of course, involved a lot of studying different systems, but as far as physical and mental training, a lot of cardio, a lot of weightlifting, and a lot of relationship building with my crewmates. Over.
Max here on behalf of Stella. How does the microgravity within the ISS affect the susceptibility to disease and the growth of plants? Over.
Microgravity does different things to different organisms. I mean, for humans, it weakens our immune systems, where something we're still studying. For plants, we do study how they grow. You know, with being in space, there is no up or down, and so it's interesting to watch plants grow towards their nearest light source. Over.
Kasha here. What are the emergency procedures if something were to happen on board the ISS? Over.
So we are trained to respond to all sorts of emergencies. The big three are fire, ammonia, and depressurization. And so we have memorized responses. All the crew members know what we're supposed to do. And in a pinch, we do have our spacecraft to be able to depart from the space station if we needed to.
This is Jade. What kind of research is being conducted on the space station and why is it important? Over.
Currently, we are running experiments that are studying everything from human biology, climate science, materials, physics, and even combustion, all microgravity. And the space station is the only place to run these kinds of experiments without that variable of microgravity. And so understanding that is going to improve life back on Earth and also help us get further out into space. Over.
This is Ruby. If you could design anything to add to the ISS, what would it be? Over.
Ruby, I love this question. I would either have an artificial gravity, like a big centrifuge installed so I could have some gravity, or I would love a greenhouse so I could build, have some plants to eat. Over.
This is Zara. How does the human body respond to the various changes in space? And when astronauts return, what symptoms do they experience as their body acclimates back to gravity on Earth? Over.
So without gravity, our bodies begin to atrophy, our muscles and our bones, but we do have countermeasures for that. We work out every single day. But one thing that we also do adapt to is the vestibular system. Without gravity, our brain gets very confused on what's up or down, and so that turns off. But when we get back, it turns back on, and it can lead us to feel very, very sick for the first hour, or the first just a few days, actually. Over.
Less than 1 minute before loss of signal.
Max again. What studies are being conducted on the ISS to measure radiation levels, and how does that impact human space exploration? Over.
Max, we've got radiation detectors all over the space station, and I'm even wearing one. And so we look at those levels and see how it affects our bodies and how that's going to affect future missions. Over.
Thank you. Before we lose the signals tonight, I'd like to say thank you, and 73 is the amateur sign of good luck and good wishes to Johnny Kim and the ISS crew from all of us here in Brisbane, especially all our students from the Wavell State High School. We wish you safe travel on the ongoing voyage on the ISS crew. Good night, 73, signing off and clear from Brisbane. Good night, everybody.
This is the International Space Station in the blind. This was a great conversation. Thank you so much, and I wish you all the very best.
MA1SS, this is Victor Kilo 4, India Sierra Sierra. We've now lost signal. We've now approached LOS. 73 Johnny, thank you very much for the contact. It's been a real pleasure talking with you. And all the best from Wavell State High School and the QTech Conference. This is VK4 ISS now out. 73. Ladies and gentlemen, Ladies and gentlemen, we just shared a wild moment of history. Amateur radio station VK4 ISS, operated by Shane Lynn, contacted astronaut Johnny Kim, KJ5 HFP, operating NA1SS aboard the International Space Station, and spoke with students from Wavell State High School attending the annual QTech Amateur Radio Technical Conference in Queensland, Australia. Now for the international volunteer of ARISS, including the amateur radio satellite corporations around the world, the American Radio Relay League, the Canadian Space Agency, the European Space Agency, the Japanese Space Agency, Roscosmos, and NASA. This is Stephen Busolo, VK4SJV, sending my greetings to you all in amateur radio terms, 73, which means best wishes. Conference operator, can you please stop the recording?
It is stopped.
Thank you, Julie. Well done, everyone. Yes, that was excellent. All very clear and some great responses there from Johnny. Okay, how's everything there at Wavell?
Yeah, very good, thanks.
No worries, thank you. Just checking. Just making sure everybody was still with us. Some really good questions there from the students, and I hope that you enjoyed the amateur radio experience. It was a pleasure to deliver. 7 threes to everyone.
Before we all go, does anybody in the room have any questions about anything they've heard, anything about amateur radio? We're always looking for new radio hams, and we're in particular for new young radio hams. So has anybody got any questions that they haven't understood or they'd like us to try and fill in some background? Otherwise, I think you all did a fantastic job this evening. You really did. You really stepped up to the mark, and your school and we are all very proud of you.
Yeah, well. The choice of Mackay, is that the setup up there, or the fact that the pass was pretty much going straight overhead on Mackay, or
It's probably the other way around. The ground station is in Mackay. It's one of a number scattered around the world, which will pick up the best orbit, and we selected the orbit of the space station that would best connect to that station in Mackay. Well, our biggest fear is that we had a power cut, to be honest, and that would have been a bit of a downer, I must say, if we'd lost contact. The bit that was most at risk was probably our broadband connection to Mackay rather than the radio connection. That always works, but the bit that got us to the ground station was the bit that we were worried about. But it didn't, it worked. Well, I'd just like to thank you all for coming today. In particular, I'd like to thank all the students and the school for participating with us on this joint project. It's taken 18 months of planning to get it to work, and I think it's shown great success from our perspective as radio hams and from your perspective as students in the school. We thank you all very much for joining with us to make this sort of thing happen. It really is something pretty special, I think. Good night to you all. Thanks for coming, and safe travel home in the bad weather.
Okay, Shane, we'd like to drop the link. Okay, good night. Okay, good night all. I'm going to disconnect now, so I'll catch you all later. Thank you for your efforts there as well, Julie.
You're welcome. Great call.
Thank you all. Have a good evening.
Take care.
Okay, bye.
Thank you very much, gentlemen. Brilliant. Thank you. That's a really good opportunity. You're on this.
I enjoyed just sitting along and listening. Not even getting to ask a question.
But yeah, thank you. No worries. Really appreciate it.
Thanks for
All right, just try and get him this way.
Congratulations. As I said to everyone, I think I'm going to murder a beer now. Yeah.